Okay, welcome to my video on collision theory and rates of reaction. This has been one full question on the chemistry paper for the last few years, and what I've noticed is that the question is always based around the idea of calcium carbonate reacting with hydrochloric acid, and then of the three parameters that you can change to affect the rate of reaction, they just change the one that they assess each year. So we're going to do each of them side by side. So I have three different sections divided out on my page here to accommodate that. And we're going to start with the word equation for what the reaction actually is. So the word equation, but there's three ways to represent reactions. You can use a word equation, you can use a symbol equation, or you can use particle theory. So word equation, symbol equation, or particle theory. So I'll try to put them all beside each other there. So the word equation for this particular reaction, it's marble chips plus hydrochloric acid. So marble chips in chemistry are known as calcium carbonate. So calcium carbonate plus hydrochloric acid goes to or forms calcium chloride plus carbon dioxide, which is a gas in this case, plus water. Now just a little bit about that word equation. Any compound where you have a metal, which in the majority of cases the first element is a metal, and a non-metal species, this is referred to as a, well in this case because it's a carbonate, then it's a metal, referred to as a metal carbonate. Now metal carbonate will produce a gas, and as should be intuitive enough to see that if it's a metal carbonate, it will excuse me, it will produce carbon dioxide gas. So just remember that. And so every time you have a metal carbonate plus acid, you get a salt, which is your calcium chloride. So that's a metal, which would be the positive ion, and a non-metal, which would be the anion. So that's your salt. You get carbon dioxide every time plus water. So that should help you memorize the word equation and also the symbol equation. Now the symbol equation, calcium carbonate, you guys should be able to form this by combining the ions from your table of ions on your resource sheet with your exam paper. But calcium carbonate is CaCO3, hydrochloric acid is HCl, lowercase l. Going to calcium chloride, CaCl2, and you guys should understand why it's CaCl2 at this stage, plus carbon dioxide gas, everybody knows the CO2, plus water, H2O. Now just to make that equation balanced, because all symbol equations should be balanced, if you look at the number of chlorides here and the number of hydrogen ions, we have 2 on the right hand side of chlorides and 2 hydrogen ions. So to get 2 on this side, we just put a large 2 there, and that shows that you multiply both of those ions by 2, and then you should have 1 calcium, 1 carbon right there, 1 carbon, and 1, 2, 3 oxygens, and 3 oxygens right there. So that's your balanced symbol equation for the exact same reaction. Just an additional piece of information which is really useful to chemists is to add state symbols. Now the state symbols are S is for solid, G is for gas, L is for liquid, and then there's a fourth state symbol which is AQ, which stands for aqueous or aqueous, and that just simply means dissolved in water. So if you guys are used to seeing hydrochloric acid on the label it says dilute hydrochloric acid, what that means is you have acid which has been diluted with water, so we write aqueous beside that. And the calcium chloride is not a solid, you can't see it at the end of the reaction, so then we write aqueous as well. Now this is important because the aqueous means that they're actually dissolved in water. So if we use particle theory, the calcium carbonate is a solid to start with. So what happens when we add the acid to it is that the particles also break up, the ions also break up in the water from the acid. So particle theory is as follows. You have a calcium ion, you're going to have a carbonate ion, and they both come from the dissociation or the dissolving of the calcium carbonate in the diluted acid. from here you get two of these ions, H plus ions, and just put circles around them to show that they're actually particles. And then you have a chloride ion, so the HCl breaks up in water, and you have two of them right there, so therefore you need to represent those particles as well. So they are your collectively referred to as your reactant particles. They're your reactant particles. And then these particles need to collide together, and this brings in the idea of collision theory. So they need to collide together in the correct orientation in order to form products. So I'm just going to put down the key terms that you need to consider when using collision theory to explain these reactions. So collision theory key terms, we should be talking about reactant particles colliding, specifically reactant particles. You should be talking about particles colliding with the correct orientation. So it's the idea that if the particles aren't facing each other in the right way, then it doesn't matter if they collide with each other, there'll be no reaction. A bit like a key needs to fit into a lock in the right way. Then you have if the particles are colliding with correct orientation and enough kinetic energy, so you need to talk about energy of particles, you'll get a successful, or sometimes referred to as effective, collision. And then if you do increase the amount of effective collisions or successful collisions, then the rate of reaction should increase. And some of you guys were asking me why this was important to chemists. Well, if you're working in industrial chemistry or any line of chemistry and you want the rate of production of products to increase, then you have to look at the various things that you can change to make that happen. So you can change the size of the particles. So you can change the size of the calcium carbonate. You can change the concentration of the acid, or you can change the temperature which the system is subjected to. And that's what we look at now in a minute. Just to complete the particle diagram for the products, so if your calcium ions successfully collide with two chloride ions, then they'll form calcium chloride, and we can represent that like this. So large calcium ion, two chloride ions stuck onto it. Make sure that when you do your particle representation that they're joined together there to show a chemical bond. That would be an ionic bond specifically. And the carbon dioxide then is a carbon atom with two oxygen atoms stuck onto that. So there's your carbon dioxide, and then your water can be represented like that. So that would be a completed particle theory. And I like teaching students particle theory to help them understand how equations balance out. Because if you take, for example, the fact that we have one calcium ion here, you should be able to find just one calcium ion on the right-hand side. Whereas if we have three oxygens here, 1, 2, and 3, we should be able to find 3 on the left-hand side. Now, what I mean by the left-hand side is to the left of the arrow there. So everything to the left of the arrow is the left-hand side, and then this would be the right-hand side. So if we have 3 oxygens identified, 1, 2, and 3, we should be able to find 3 on this side, and we do. The 3 oxygens are contained inside the carbonate polyatomic ion. So that is they're the 3 ways of representing the reaction. Now, just to quickly show you how this was performed experimentally, because we did this in the lab for the first lesson. We looked at how to do this experiment, how do you trap the gas, etc. So the experiment was set up, involved the following pieces of equipment. You had a boiling tube. Inside the boiling tube, you would have had your hydrochloric acid, which is aqueous. You would have put in your calcium carbonate, CaCO3, which was solid initially, but then would break up in the water. You had a rubber bung, BUNG, in case there was any confusion about that. A delivery tube, which just delivers the carbon dioxide gas across to the other side. And then you have an inverted or upside down measuring cylinder, CYLINDER. And then the measuring cylinder was inside a basin of water, and the idea was that the bubbles of gas collected would displace the water out of the measuring cylinder, and you could measure the volume of CO2 gas produced. And then this is a way for measuring the effectiveness of your reaction. Okay, so then what we looked at was I went through the exam papers and discovered this trend that in 2013 they talked about changing surface area or size of the calcium carbonate. In 2012 they looked at changing the temperature on the system, so the temperature that the experiment was carried out at. And then in 2011 they looked at the concentration of the HCl. So we're going to take each of these 3 years now, and we're going to look at the exact same reaction, same word equation, same symbol equation, and we're going to discuss why you get the results that you get using particle theory. Okay, so let's talk about surface area, or the size of the calcium carbonate that you use. Well, the basic idea here is that if you have a large piece of calcium carbonate, so let's represent it like that. So this is calcium carbonate, solid to begin with. If we just think in 2 dimensions, so there are then going to be 1, 2, 3, 4 surfaces exposed. So 4 surfaces exposed. Now, what are we exposing them to? Well, we're exposing them to the hydrogen ions and the chloride ions from the HCl acid. And there, that's the other reactant particle. So 4 surfaces exposed to collide with the HCl particles. First is a situation where if we break that piece of calcium carbonate down into 4 smaller pieces, remember we're only thinking in 2 dimensions here, you would have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So 4 times 4, 16 surfaces exposed. So you have 4 times the surface area just from making the particle 4 times smaller. And as a result, there are 16 surfaces exposed to the hydrogen ions and the chloride ions, and therefore the rate of collisions should increase. Rate of collisions increases. And that's the basic concept of decreasing the size of the particle. So if you decrease the size, you're decreasing the size, you increase the surface area. And that's the concept there. How do we talk about that using collision theory? Well, we need to consider use of some of the key terms. I'm just going to put a graph in here. This is the rate curve, which comes up again and again and again. So you must be familiar with this. Now, I would recommend using a ruler if you're drawing this in your books. Time is going to be on the x-axis, and then there will be some measure of the amount of CO2 that's produced. So it could be volume of CO2, because remember that's the gas that we're measuring in the measuring cylinder. It could alternatively be the loss of mass as the CO2 escapes from the boiling tube. So it depends what the exam paper, what way they want to represent it. But in either case, this is a measure of the rate of the reaction. And then if you have a small surface area, then the rate of the reaction, it's going to be much faster initially, and then it reaches its endpoint. If you have a smaller surface area, so larger chips, then it's not so fast to begin with, and then it slows down. It takes longer to reach its endpoint. So this would be large calcium carbonate, and this one here in pink would have been the small calcium carbonate. So there are 3 sections to rate curve, and this applies to temperature or concentration as well. The first section right here is an initial fast rate of reaction, and that's because you have lots of reactant particles, essentially. Lots of reactant particles, therefore they can collide together and have effective collisions. The second section is, I like to call it rate is slowing down. So that's slowing down, and that's because you're starting to running out of reactant particles. And as I've mentioned in class, this is going to really be the specifically the H plus and the Cl minus particles that you start to run out of, because you had quite a low concentration to begin with. The amount of calcium carbonate that was added is quite huge in comparison. So the rate starts to slow down because you run out of acid particles. And number 3 then, section 3 is the flat line. So the reaction comes to completion, reaction ended, and there's no more collisions, no more effective collisions. No more effective collisions taking place. So just a little bit to add then regarding collision theory for the surface area paragraph. You need to mention that if you decrease the size, you increase the surface area exposed. Therefore, you have more effective collisions. More effective collisions between the reactant particles, and therefore the rate of reaction increases. Okay, so if you want a full in-depth coverage of how to answer these questions, you guys just look up the 2013 exam paper. Now there'll be no sample answer for that because it hasn't been released yet, but you can look up the 2012, the 2011 one. It'd be very similar stuff, and we can talk about that in lessons as well. Next concept you can look at, or the parameter you can change, is temperature in the system. Now the key concept with temperature in the system is the fact that if you give more heat energy, then you give more kinetic energy to the particles. So more heat energy gives more kinetic energy to the particles. So it's the equivalent of looking at hydrogen chloride trying to collide with calcium ions at a low temperature. They're at a low temperature, then they have very low kinetic energy. They're colliding with each other, but it's not with much force, and therefore the collisions are not very effective. Versus a situation where you subject them to a higher temperature, and then the particles are colliding together with far more force. So that's represented like that, really aggressive, good collisions, and therefore you have more effective collisions. More effective collisions, they are more frequent, and therefore the rate of the reaction increases. And then it's the opposite scenario for the low temperature. You have less effective collisions, you have they're less frequent, and therefore the rate of reaction will decrease. And then that can be represented on the same sort of rate curve as well. So in this case, we're looking at temperature. How does temperature affect the rate of a reaction? So we still have time on the x-axis, volume of CO2 produced or mass of CO2 lost. If you're at a low temperature, then the rate of the reaction will not be very fast. If you're at a higher temperature, then it will be faster. So this would be high temperature, and this would be low temperature. And you can use the same concepts we had here for surface area to explain what's happening in the rate curve for temperature. So the concepts start to repeat themselves a little bit. The last concept we need to look at, and we'll actually teach this next week, but I decided to put it into the video here, was concentration of HCl acid. So if you have more HCl, you have more reactant particles, and therefore you have more frequent collisions. So you have more frequent collisions, and you also have an opportunity, since you've increased the quantity of one of the reactants, you have an opportunity to increase the amount of product, and in this case CO2 produced. So in the other two cases, we didn't change the quantities of the calcium carbonate, or the temperature wasn't changing the quantity of either of the reactants, so you still get the same amount of carbon dioxide, and you can see that both graphs finish with the same amount right there. But the graph for this situation with extra hydrochloric acid should give you slightly more CO2. So if I do the graph really quickly, with low concentration of HCl, so concentration off can be represented with these square brackets. So low concentration of HCl, initial fast rate of reaction starts to slow down and then stops here, where this is the amount of CO2 produced, CO2 gas. But if you use a higher concentration of HCl, you should get more CO2 produced. So there's a separation in the endpoint for the two graphs there. So this is a high concentration of HCl, and this was a low concentration. Now, how do you represent that pictorially or with a diagram? Well, it's essentially going to be a situation like this. You have your boiling tube to start with the rubber bung on the top and the delivery tube. And if we have two situations, a high concentration of HCl is going to basically mean lots of H plus and Cl minus ions crammed into the container, and therefore you have more opportunity for collisions with calcium and chloride ions, or calcium carbonate ions rather. Whereas if you have a low concentration of acid, let's just make it really obvious, then you have very little of the H plus and the Cl minus reaction particles. So that is an overview of the three ways to affect the rate of a reaction. As I've pointed out here, hopefully you can see that they come up regularly in the exam papers. This is one entire question. It's a question you should do really well on because chemistry repeats itself from year to year. Even the equation that they look at is the same from year to year. So you guys need to really familiarize yourselves with this equation of calcium carbonate plus hydrochloric acid making calcium chloride plus carbon dioxide and water. You must familiarize yourselves with the key terms to use when you're using collision theory to describe what's happening. And you must be really familiar with this idea of particle theory as well. And if you do that and understand three sections of your rate curve, which is down here, that's your rate curve in each case, you should do quite well on that question. So that's my video on rates of reactions. Next week, we'll practice answering exam questions. We'll have to do a bit of revision in preparation for the end of unit test, and then we'll come back to the second half of the chemistry topic in term 3.